Hey everyone, I just wanted to hop on here really quickly and give a review of my article using quantum computers to price options. Of course, as always, the article will be the top link in the description. So if you do want to read it, make sure to head down there and check it out on my Medium. So our first step to pricing options is really understanding what exactly an option is. So an option is a financial contract that gives the holder the right, but not an obligation, to buy or sell a financial asset at an established price in a given time frame. So of course, I go through the different types of options here. We have a long call, we have a short put, and of course, you can read more about these in the actual article. A lot of the intuition on why options, why not just purchase the shares I'm interested in or short the shares that I'm interested in, and what advantages do options provide to me. So there are obviously a few that you might want to read about. And a lot of the problem that we face when pricing options is actually pricing the premium and determining how much I should pay for the right to buy or sell a certain underlying asset in the future. And that's the big question. And there are a variety of factors that go into determining this question. And just a few include the actual underlying value of the stock, the time value of the option, and the implied volatility of the underlying stock. And a lot of the questions that come boil down to this bottom line is, do I make money by buying this option? And that's a key question that we have to address. And obviously it's the key existential questions behind the options, right? And a lot of the banks spend a lot of their days trying to find better models to actually answer this question. Of course, one of the most famous formulas was Black-Scholes Merton, perhaps one of the most famous formulas of modern finance that gives you a simplified version of how to derive the fair value of an option. Again, it incorporated Brownian motion to the movement of markets, which was a powerful realization and a first of its time. And that's essentially why it won a Nobel Prize in economics. And then we have Monte Carlo, which is essentially just creating a bunch of random price paths, finding the average over those paths, and determining a fair value from there. Again, this remains the most effective classical way to price complex path-dependent options, where you actually need to know the exact path an option follows. Again, there are like even different types of options that are more complex than this. Here we have a barrier option where it actually needs to cross a certain predetermined barrier to actually be able to be exercised. And of course, there are many others. Again, quantum amplitude estimation is one of the ways that quantum computers have been proposed to actually effectively price options faster than classical algorithms have been able to previously. And if we look at this equation here, where m represents the number of quantum samples used, we're taking that scale from O of 1 over root m classically to O of 1 over m using quantum computers, and where we're actually using the number of errors. So you can imagine if m was at 1,000,000, so 1,000,000 quantum samples, classically we would get 1 over 1,000 error scaling, whereas using quantum computers we would get 1 over 1,000,000 error scaling, which is already quadratically better. And that's a lot of the reason why quantum computers have been proposed as a potential solution to pricing harder to price options. So laying out the great groundwork, again, we have 3 steps to follow when pricing options on a quantum computer. Loading the probability distribution, and then we have circuits to compute the payoff, and we have amplitude estimation that comes next. So essentially all we're doing here is creating an operator A, and we're encoding the fair price of that option onto this little amplitude root A, and that will turn into a probability once we square it using the quantum Born rule. And again, we just set A to this expectation value of this f of x, and that's exactly what we need to solve for to actually find the fair price of the option. Again, we saw that a lot of the options have linear payoffs, so we just encode that linear payoff onto an ancilla qubit. We do some binary conversions to make sure that our rotations actually scale correctly. That's all this is. And we can visualize that as a bunch of controlled by rotations. Again, we have some scaling. So we have f tilde of I, which is a scaled version of f of I, to create asymmetrical functions rather than functions that map to 0 and 1, and some additional scaling parameters depending on what kind of error you want to achieve. Again, we're given a probability of finding the last qubit, the ancilla qubit in the one state, given as this, and through a bunch of mathematical manipulation, we can find that the probability of finding the ancilla qubit in the one state is given by this formula, with fmax and fmin with these definitions. And we can find that the convergence of amplitude estimation is actually given as m over -2/3. And this is already better than classical methods, but to recover the actual full 1/m convergence, you would need more gate depth and more accurate values of C, which again will come as you approach beyond NISQ era to fault-tolerant quantum computers. And again, we can recover the expectation value f of x because we know fmax, fmin, and C, and that's the only unknowns here that we need to solve for. Again, just a rundown of amplitude estimation. Again, there are other resources on this in itself. Again, we encode this little a, root a, on this one state on the ancilla to be our probability of finding the option in the one state, which is again the fair value. So just a bunch of tricks using quantum phase estimation without using quantum phase estimation. We construct a Q operator that acts as essentially a rotation of 2 theta a in the two-dimensional vector space spanned by psi 0 and psi 1. So that would look something like this. If we look down here, scroll through this article, we're essentially creating this 2 theta a. So we have theta on this side and theta up here, and we rotate it every time 2 theta closer to this fair option price over here. And you can imagine that we're solving for psi 1 for W and psi 0 for this S. Again, just some quantum amplitude estimation tricks, not to use quantum phase estimation. And we can actually use these with maximum likelihood approximation to get a good estimate for theta A and then A, which encodes the fair undiscounted value of the option in the amplitude of 1 in the ancilla qubit. Again, with practical applications, you can do this through Qiskit, Cirq, PennyLane, whatever you want, to actually create these circuits. So to price European call options, again, we construct a payoff, which is essentially the difference between the spot and the strike, or zero, and it's the max of these. So either you make no money or you make the difference between the spot and the strike, if the spot is again greater than the strike. So to actually check whether the spot is greater than the strike, we use a comparator qubit C, which we have encoded in this last ancilla qubit. Then this is just a bunch of quantum adder circuits to compute the addition of qubit I and binary digit T of I into AI rather. And you would need actually a register of AI ancilla qubits, again, depending on the number of qubits you have in your original register. After computing all the carries, you get some psi n, which will only be greater than or equal to the strike if there's a carry in the last and most significant qubit. Again, this is just a practical application of it, just an example. And we have a payoff, right? So if I is less than k, we only have this constant value, and if I is greater than or equal to k, our strike, we have a constant plus this linear payoff, which is actually what we observed when we were looking at the call option. And again, on a quantum circuit, this would look something like this, where we have an ancilla holding our answer, where the constant rotation is always implemented and the actual linear function is only implemented as a control of C, which would need to be 1, and the last register in N. And so we see what the state becomes, we see the probability of measuring them, and then all we need to do here is find accurate values of G0 and G of I, which we find here. And again, this yields the undiscounted price, which you would need to discount depending on future interest rates. But this can be done using classical hardware. It's not too hard to do. So we have this probability distribution. Once we put it onto the quantum register, this is what the payoff function looks like. Again, it should be linear, but the intervals are quite spaced out, so it doesn't look too linear. But and then as these are still fairly easy to price on classical hardware, we have an exact value and an estimated value using the quantum computer. And again, this estimated value can be brought closer to this exact value by using more qubits and using better quantum computers. Put options, same thing, just different payoff function, different actual like payoff models. So payoff function looks sort of like this, which again we saw, and same exact output. Basket options, they're essentially a weighted sum of a bunch of stocks, individual stocks, and then doing a European call. So we have this set of individual stocks, then we have this set of quantum registers that encode each of them, and we take the tensor product between each, which is just essentially having a bunch of random stocks with each other. We create this transformation, which adds a number of n ancilla qubits to actually compute the weighted sum over each of these quantum registers. Again, we have some vectors, a set of vectors which are the weights, and then a set of vectors which are the actual spot prices of the underlying assets. And again, the quantum circuit for a basket option would look something like this, where we have a weighted sum over each of the quantum registers, and then we're checking if using this comparator qubit if this weighted sum is actually greater than our strike. And then again, we encode the linear payoff function onto this p qubit controlled on this final quantum register and this comparator. And again, we just prove that this does experience a quadratic speedup over classical methods to price options. And here's an example, so we can visualize what the correlation between two identical underlyings is using a 3D graph here. We have the payoff function. Again, it looks just like a European call, and we have an exact value, an estimated value, and then the confidence interval again. Just some acknowledgements I'd like to make was the fact that this article was written based off of the work of Nikita Stamatopoulos and et al. At Goldman Sachs, ETH Zurich, and IBM, I believe, which was critical in providing the math and motivation behind the idea of pricing options using quantum computers. And a lot of the simulations in this article were achieved through Qiskit's finance module, which offers plenty of tutorials, which I highly recommend you guys to check out. With that, that's everything for today's video. Again, if you liked it, make sure to share with your friends, leave a like and subscribe, and I'll see you guys in the next one. Peace.